Let us consider motion of the body on the inclined plane. But here we are going to imagine body is rolling down the inclined plane. When the body is rolling down the inclined plane, let us say this is the case. This is the inclined plane of height, let us say h, and length is L. Body is allowed to roll down from the top. So by rolling, it reaches the bottom of the plane. From the figure, sin theta is equal to opposite by hypotenuse, or h is equal to L into sin theta. Now let us apply law of conservation of energy. When the body is at this highest point, it will have only potential energy, which is equal to mgh. But since the body is rolling down, the total kinetic energy of the body is equal to translational into 1 plus beta. Beta is called the shape constant. Since the body is in rolling motion, it will have translational plus rotational. The total kinetic energy E, this is already we discussed, ET plus ER. Since ER is equal to beta into ET, ET stands for translational, ER stands for rotational. The total kinetic energy is ET times 1 plus beta. So this we can write as half mv square into 1 plus beta. Now this mgh, instead of h, if I substitute this L sin theta, I can take it as m into g sin theta into L. Bring this 1 plus beta to this side, m into g sin theta by 1 plus beta is into L is equal to half mv square. So if I compare the equation with the linear motion, mass into acceleration multiplied by distance is equal to half mv square. This is kinetic energy. This is of course work done, ma into L. So if I compare these two equations, A becomes equal to g sin theta by 1 plus beta. So when a body is allowed to roll down from the top of an inclined plane, its acceleration is given by g sin theta by 1 plus beta. Sliding case, there is no dependence on the shape. Whatever the shape might be, acceleration is g sin theta. If I imagine rolling, it depends on the shape constant beta. Which is the shape constant? So all the bodies are not going to roll down with the same acceleration. Disc, ring, sphere, solid sphere, hollow sphere, etc. Their rolling motions are, accelerations are different. Now the question is, in what time it reaches the bottom? Time taken to reach the bottom. So we know that S is equal to ut plus half at square. Since u0 I can write as 2s by a. Here it is 2l by g sin theta by 1 plus beta. This is what we call time taken to roll down the plane. So this is 2l by g sin theta into 1 plus beta. Similarly, the velocity gained by the body, v square minus u square is 2as, but anyhow u0. Therefore v is equal to root over 2as. Present case 2 into g sin theta by 1 plus beta into L. So here v inversely proportional to root 1 plus beta. But whereas a time, if I take, time is directly proportional to root 1 plus beta. Beta is the shape constant, and the dependence on shape is there for time as well as velocity gained.